Hey everyone. In this lecture, we're going to cover section 3.3, applications of the standard deviation. So in the previous lecture, really the previous two lectures, I went over section 3.2, which covered measures of variability, specifically the range, the variance, and the standard deviation. And we're going to focus now on how do we apply the standard deviation in this section. So just a quick reminder, the standard deviation measures the average deviation from the mean. So suppose we're looking specifically at a bell-shaped distribution. We have what's called the empirical rule. So now this empirical rule applies specifically only to a bell-shaped distribution. So let's say we have a data set, it follows a bell-shaped distribution. Then we can say that this is how the data values are going to be approximately distributed. So if we look at this picture for a minute, and I'll go over these bullet points in a second, they really correlate to the picture that I have here. So sometimes I think it's easier to look at a picture first. So what the empirical rule is saying is that if I have a bell-shaped distribution, and remember in a bell-shaped distribution, the mean is in the center. So notice how I labeled the bottom axis or the horizontal axis. The mean is in the middle, but remember, there's two symbols for the mean, either the population mean or the sample mean. So we listed both here. So in the event that we were working with sample information, we would use X bar as the mean. If we were using a population of data values, then the mean would be mu, right? We use different symbols. And then don't forget also the standard deviation for a sample is represented by S. S represents the sample standard deviation, and sigma represents the population standard deviation. So I have a row for both instances. So the way this bell-shaped distribution is being divided up is by adding one or subtracting one standard deviation from the mean. So if I have the mean in the middle, whether it's the sample mean or the population mean, and we add one whole standard deviation like we did here, and then we subtract one whole standard deviation, I went an equal distance, right, on both sides of the mean. I went one standard deviation above and below the mean. We expect, based on this rule, about 68% of our data values to fall within one standard deviation of the mean. And again, this is an approximation, so that's why I don't have an equal sign here. I have an approximation sign. So we expect approximately 68% of our data values in a set to fall within one standard deviation of the mean. Now, suppose we were to add two standard deviations to the mean. So what if I took the mean and I added two standard deviations? So either two sets of S or two sets of sigma, depending if we're working with a sample or a population. And then I subtracted two standard deviations. Now we would expect approximately 95% of our data values to be within two standard deviations of the mean. That's almost everything, right? That's almost all of our data. Because imagine shading the entire bell-shaped curve here. We would shade 100%, right, of our data values. So this takes up a big chunk right here, this 95%. So we say we would expect about 95% of our data values to fall within two standard deviations of the mean. Now, suppose we were to add three standard deviations to the mean and we subtracted three standard deviations from the mean. Now we would expect almost all, or approximately 99.7% of our data values to be within three standard deviations of the mean. And that's almost 100%, right? 99.7% is almost 100%. So we would expect about 99.7% of our data values to fall within three standard deviations of the mean. So then what do you think we would consider any data value that falls beyond 3 standard deviations from the mean, whether it's more than 3 standard deviations above the mean or more than 3 standard deviations below the mean. We would consider that an unusual value, right? A value that's probably extreme compared to the rest of the values. And remember what we call those? We call those outliers. So we would expect any potential outliers to fall more than 3 standard deviations away from the mean in a bell-shaped distribution. And I'll write that down. So I'll put a little note here that we will consider a data value that falls more than 3 standard deviations away from the mean, an outlier. And this is in a bell-shaped distribution. So that's the rule. We're going to consider a data value that falls more than 3 standard deviations away from the mean, an outlier, specifically in a bell-shaped distribution. So we expect 99.7% of our data values to live within 3 standard deviations away from the mean. And this set of rules is called the empirical rule. So let me make this a little bit smaller. So what I have summarized on top here is what I just went over in a picture, but in words. So this first bullet says we would expect approximately 68% of our data values to lie within 1 standard deviation of the mean. We would expect approximately 95% of the data values to live or lie within 2 standard deviations of the mean. And we would expect approximately 99.7% of the data values to lie within 3 standard deviations of the mean. And then any data value that lies more than 3 standard deviations away from the mean, we're going to consider it an outlier. So why don't we do an example now so we could see how we apply this empirical rule. And actually, before we do that, let me just add some notes to this picture that I think are going to be helpful to you. So let me just delete what I have drawn here, and then I'm going to label some smaller areas within this distribution. So imagine, because this is going to be helpful when we answer some questions in a minute and then in your MyStatLab homework questions. So imagine I took this 68%, this area that's 68%, and I divided it in half. Half of 68%, right? So 68% divided by 2 is going to be 34%. So we can say each one of these little chunks here is about 34%. Now, what if I wanted to label these 2 areas where I put the question marks? What would those be equal to? Well, I know from question mark to question mark, right? So if I went 2 standard deviations below the mean to 2 standard deviations above the mean, that's going to be about 95%. But this middle chunk here, we already know is 68%, right? If I go 1 standard deviation within the mean. So if I take 95% and I subtract 68%, I'm going to get 27%. So 27% of my data values are going to land within these 2 areas where I put the question marks. And both these areas are equal, so I'm going to divide 27% by 2, and I'm going to get 13.5%. So each one of these little areas here where I had the question mark is about 13.5%. So now if I want to get these little areas where I'm going to put the question marks, I'm going to take 99.7% and I'm going to subtract 95%. And then that's going to leave me with 4.7%. And we're going to divide that 4.7 in half because that's what each one of these little areas with the question mark is going to be equal to. So 4.7% divided by 2 is going to be equal to 2.35%. So these little question marks here, these areas are going to be about 2.35%. And then last, these teeny tiny areas out here where I'm shading in these tails where we go beyond 3 standard deviations from the mean, they're each going to be 0.15%. And the reason is, so let me get rid of this. We don't need this anymore. So the reason is that if we go 3 standard deviations above and below the mean, that's about 99.7%. We only have 0.3% left, right, to get to 100% if we were to shade the entire curve. So there's 0.3% left over. And if I divide that in half, 0.3 divided by 2 is 0.15. So those two areas are each 0.15%. So this is how we can slice and dice this bell-shaped curve in terms of area. So now let's apply this to an application question. So let's look at example 9. The results of a standardized achievement test are approximately bell-shaped with a mean or sample mean equal to 350 and a sample standard deviation S equal to 85. According to the empirical rule, approximately what percentage of test scores would you expect to fall between, and then I have a bunch of questions. So A says 265 to 435, B says 180 to 520, and so on and so forth. So before we can answer these questions, we need to sketch a picture, right? Because I need you to envision, what do these tests look like, right? Well, I have a really important piece of information right here. It says test scores are bell-shaped. And I also told you the mean, which is 350, and the standard deviation, which is 85. So we can draw a picture with that, right? So why don't we go below and let's sketch what this would look like. So I'm going to sketch my bell-shaped curve, and X bar is going to go in the middle, and X bar is equal to 350. And one standard deviation is equal to 85, right? S is equal to 85. So let's break down how these scores are distributed. So what would be the test score that's one standard deviation above the mean? So what if I took the mean and added a standard deviation? So in other words, what's 350 plus 85? That's going to be equal to 435. So that would be a test score of 435. Now, what if I took the mean and I subtracted S, or one standard deviation? So what if I took 350 and I subtracted 85? We're going to get 265. Now, what if I added and subtracted 2 standard deviations from the mean? So what if I took the mean and I added 2 standard deviations, or 2 sets of S? So that's going to be 350 plus 2 times 85, which is going to be equal to 520. And then what if I took the mean and I subtracted 2 standard deviations. So if I took 350 and I subtracted 2 sets of 85, I'm going to get 180. And now let's go 3 standard deviations above and below the mean. So what if I take the mean and I add 3 standard deviations? That's going to be 350 plus 3 sets of 85, which is going to be 605. And now let's subtract 3 standard deviations from the mean. So that's going to be 350 minus 3 sets of 85. And that's going to be 95. So these are how my scores are distributed in this distribution. And we can assign percentages to these, right? Because now we know about the empirical rule. So we know that we would expect approximately 68% of our data values to be within 1 standard deviation of the mean. The empirical rule tells us that we would expect approximately 95% of our data values to be within 2 standard deviations of the mean, and we would expect approximately 99.7% of our data values to be within 3 standard deviations of the mean. So now we're ready to answer some questions, right? Now that we know how these scores are distributed. So let's look at part A. So part A says, what percentage of test scores would you expect to fall between a 265 and a 435? So I'm going to change colors here. So here's a 265 and here's a 435, right? That's where my 2 scores are. And both of those fall 1 standard deviation away from the mean. So we expect about 68% of our data values to fall between a 265 and a 435. Now let's look at part B. So part B says, what percent of our scores would we expect to find, or would we expect to fall between a 180 and a 520? So let's circle 180, let's circle 520, and both of those scores happen to be 2 standard deviations away from the mean. So we expect about 95% of our scores or our data values to be between a 180 and a 520 based on the empirical rule. So this is going to be about 95%. Now let's look at part C. So part C says, what percent of our scores would we expect to fall between a 95 and a 605? So here's a 95, here's the 605, and both of those scores are 3 standard deviations away from the mean. And our empirical rule tells us that we would expect about 99.7% of our data values to fall within or between 3 standard deviations from the mean. So this is going to be approximately 99.7%. So let's continue. So part D says, what percent of our data values do we expect to be between a 265, so let me circle 265, and a 520, which is right here. So now this is a little bit different than the previous ones that we did, because a 265 is 1 standard deviation below the mean, and a score of 520 is 2 standard deviations above the mean. So now we're looking at this shaded area, right? So the area that I just shaded in red contains the scores that are between a 265 and a 520. So we need to know this little piece here, right, of shaded area, because I already know from 265 to 435, that's 68%. But we labeled that up here. Remember when we broke down the little slices within my bell-shaped curve up here? So this little area is about 13.5%. So this, and let me do this in a different color so we could see it. So this is about 13.5%. And now we could just add the total area, right? So this is going to be about 68% plus that 13.5%, right? So we're going to add the two together. So 68% plus 13.5% is going to give us about 81.5% of the scores we would expect to be between a 265 and a 520. Part E says, what percent of the scores do we expect to be between a 95 and a 265? So I circled those two scores. And let me shade that area that we're looking for. So I'll use yellow this time. So we want to find the percent of the scores that live between a 95 and a 265. So we need to label those shaded pieces, right? And we know this piece right here is about 13.5%. And the smaller piece over here is about 2.35%, right? Based on what we calculated in our diagram above. And now we could add those two shaded areas together, right? So we're going to get approximately 2.35% plus 13.5%. And that's going to be approximately 15.85%. So we would expect about 15.85% of our test scores to be between a 95 and a 265 in this distribution. And now we have one last part to answer. So part F, change back to red here so we could see that. And let me just erase this so we could see better. So the question says, if there was a test score equal to a 625, would you consider such a score an outlier and explain? So where would a 625 go if it were on this distribution? So if there was a score of 625, it would go to the right? It would go past 605 because you see how we have 605, that's the data value, that's 3 standard deviations above the mean. A 605 would lie out here, right? Let's say out here, I'm sorry, 625 would be about out here. And remember what we consider a potential outlier. We consider a data value that falls more than 3 standard deviations away from the mean a potential outlier. And that score of a 625 does fall more than 3 standard deviations away from the mean. So yes, we would consider it an outlier since it falls more than 3 standard deviations above the mean. And that's our rule, right? So this was a nice example as to how we can apply the empirical rule when we're working with a bell-shaped distribution. And you'll have more practice with this in the homework questions that I give you in my stat lab.